Earth scientists study processes that occur in the intersection of the four major Earth spheres. The hydrosphere, which involves all water on Earth in solid, liquid, or vapor form. The biosphere, which involves all life on Earth. The geosphere, which involves the solid part of the Earth from its surface to its core. And the atmosphere, which involves the layer of gas that envelops the Earth. In this unit, we will focus on applications of the unit circle, trigonometric functions, and right triangles. Earth scientists use these mathematical concepts to model and predict the behavior of our planet Earth and other astronomical objects.
In our solar system, all astronomical objects orbit the Sun, and moons also orbit their planets. Most orbits are not true circles, but are slightly elliptical. The deviation of an ellipse from a circle is measured using a dimensionless quantity called eccentricity. Changes in the eccentricity of Earth's orbit around the Sun occur periodically over thousands of years. These changes are predictable and can be modeled with sine and cosine functions of time. Changes in the eccentricity of the Earth's orbit alter how sunlight hits Earth's surface and impact climate on timescales of tens of thousands of years. Whereas changes in the eccentricity of Earth's orbit occur too slowly for us to detect in a human lifetime, other changes related to orbits affect our daily lives. For example, the Moon orbits the Earth every 27.32 days and exerts a gravitational pull on ocean water enveloping the Earth. The gravitational pull of the Moon, along with the Sun and forces related to Earth's rotation, create a tidal bulge in Earth's ocean directly below the Moon. The Earth rotates in and out of the tidal bulge, causing ocean waters to rise and fall as tides. Tides are the longest waves in the ocean, with a wavelength up to half the Earth's circumference, or up to 20 kilometers, in a period of either 12.4 or 24.8 hours, depending on location. High tides and low tides follow a periodic pattern that can be modeled at a particular location using a series of sine and cosine functions shown here.
Other planet-moon systems have tides, including Saturn and its icy moon Enceladus, shown here. Enceladus is one of the brightest solar system objects in the night sky because its icy surface reflects a lot of sunlight. The gravitational force of Saturn on Enceladus creates frictional heating of the icy moon, forming a subsurface ocean. These forces also crack the surface ice, allowing water to spew out from the subsurface ocean into space in so-called cryovolcanoes. NASA's Cassini mission studying Saturn was able to capture and analyze water from the subsurface ocean of Enceladus by flying through one of these cryovolcano eruptions. It found complex organic molecules in the ocean water. This discovery has spurred scientists to propose missions to Enceladus to burrow under the icy surface to study its ocean as part of our search for extraterrestrial life.
Another body in our solar system that is a part of the search for extraterrestrial life is Mars. The surface of Mars is shaped today by wind-driven sedimentary processes, similar to processes occurring on Earth. Just like on Earth, wind on Mars moves grains of sand, creating ripples and dunes. Solar wind, shown here, has blown away much of the Martian atmosphere due to Mars's weak magnetic field, substantially reducing atmospheric pressure when compared to Earth. Due to the lower atmospheric pressure, Martian wind is much weaker than wind on Earth. However, studies have shown that some winds on Mars still carry enough power to move grains of sand and dust around on the surface. Earth and planetary scientists study processes on Earth in environments that are analogous to those found on Mars. This helps them better interpret the data that comes from instruments sent to Mars like those carried on the Curiosity rover. While wind is still actively shaping Mars's surface, flowing water also created geologic features on Mars in its past. Impact craters on Mars are often infilled with sediment ejected by nearby impacts or brought into the crater by wind or water. As a result, many large craters also have dune fields within them, like those found in deserts, beaches, and underwater on Earth. In Mars's past, a large portion of the craters were likely home to liquid water, including Gale Crater, the landing location of the Curiosity rover, and Jezero Crater, the future landing location of the Perseverance rover. Mathematicians scientists, and engineers all work together on missions to explore and better understand planets and moons throughout our solar system.
Hi, my name is Dr. Rachel Kroniak, and I'm a planetary geologist at NASA's Jet Propulsion Laboratory in Pasadena, California. Planetary geology deals with the rocks and materials on the surfaces of planets and moons throughout our solar system. My work is very interdisciplinary and involves several different methods, which honestly keeps it fun and interesting. I use math in a bunch of different ways in my research. For rover operations, we're constantly having to manage our rover resources, things like our battery levels, our data allowances, and how long certain activities take, and how these activities fit into our daily timeline. I also use right triangles and trig functions when I'm working with rover images to help figure out the resolution of a particular image. The pictures that we take with the rover cameras are taken at various distances, depending on what we're wanting to point our cameras at. We know the height of the rover cameras off the ground, and also the distance to the target that we're interested in, so we can use right angles and trig functions to help us figure out how far away certain features are. In the lab, I use basic geometry all the time when I'm working with rocks. I often need to cut rocks to certain geometric dimensions too. So far, I've spent most of my time working on Mars, and I do that by working with Mars satellites and rovers to collect and analyze data. And we use these data to understand what the rocks on Mars are made out of, and how they might have formed in the past. Right now, NASA has a rover on Mars named Curiosity, and Curiosity's been exploring a site called Gale Crater since 2012. I'm a member of the Curiosity rover science team, which means I get to participate in the daily operations of the rover. Each day the rover sends us new images and data, which we take a look at first thing in the morning, and then we come together as a team to decide what the rover is going to do for the day. We make very important decisions throughout the day, such as what rocks and soils around the rover are interesting to us, are there particular targets that we think would give us interesting scientific data, and if so, which of our instruments on the rover should we use to investigate them? Once we're done investigating this particular site with the rover, where should we drive to next? All of these decisions are made with long-term mission guidelines and objectives in mind. I'm also on the science team for the Mars 2020 Perseverance rover, which is NASA's latest rover that will be launching this summer, sometime in mid to late July, and will land on Mars next February. There's a lot of planning that goes into a mission before it launches, including making sure the rover is fully built and ready to go. That's the job of our brilliant engineers. And also making sure the science team is prepared to operate the rover once it lands and starts exploring. Part of my job has been to help prepare the science team for operations. The Perseverance rover is even more complex than Curiosity, and the operations team is very busy developing the tools and processes that we'll use once the rover lands next year. I'm also helping to map parts of Perseverance's landing site. Perseverance will be landing in Jezero Crater, a crater that's quite a bit smaller than Gale Crater, but shows really interesting evidence from orbit of an ancient delta, which is similar to features that we commonly see on the Earth. Deltas are fan-shaped deposits that form when rivers carry sediments into a body of water. An Earth example of a delta is the Mississippi River Delta, where the Mississippi River enters the Gulf of Mexico and deposits sediment, forming these large lobate features. These features are actually big enough that we can see them from outer space. So we think a similar process might have happened on Mars to form the Jezero Crater Delta. So we're going to look at these features in detail using pictures from satellites orbiting around Mars. When I was in high school, I had the opportunity to attend space camp at Huntsville, Alabama, where I pretended to be an astronaut and simulated space shuttle missions for a week. I completely fell in love with the idea of working for NASA and being able to participate in space missions. In college, I became interested in geology and the planets after learning about the Earth's history and also about Mars and the other planets in the solar system. After that, I went to graduate school where I got my first taste of working on a Mars mission. Now I get to combine my geology experience and work on Mars missions at NASA, which is a total dream come true.